Hello everyone, welcome to this video on hypothesis testing. Hypothesis testing is something that we do in inferential statistics. It's a very important topic. In fact, it's meant to be the highlight of this entire class. Everything that we've done from the beginning of the class until now has been preparing us to do hypothesis testing at this point. Now, if I were to ask you, what is a hypothesis? I would bet most of you would say that it's an educated guess. And then you would be right. I think that's a good way to think about a hypothesis as an educated guess. Now, in terms of statistics, we can make hypotheses, educated guesses, about statistical matters. In this class, we're going to focus primarily on making hypotheses about the population mean. Now, a lot of the hypotheses that we encounter will fit the form of the one that you see on the screen right now. If I take some action, then I think the population mean of whatever it is I'm studying will either be less than, greater than, or not equal to the current value. So for example, let's say that right now the average score on the final exam for Math 107 students is 75. If I'm a college administrator, I might have a hypothesis in my mind that goes something like this. If I hire more tutors, then I think the population mean of Math 107 students' final exam scores will be greater than 75. That would be the kind of hypothesis we're talking about. And we're going to want to put that hypothesis to the test. We want to know, is that a good hypothesis? Is it a bad hypothesis? We're going to learn how to test hypotheses in this chapter. Now, hypotheses like the one that I just stated, and like the one that I have shown on the screen right now, are known as alternative hypotheses. Sometimes those are abbreviated with H sub 1, sometimes H sub A. Okay, alternative hypothesis. Now, if it's called the alternative hypothesis, that suggests that there is another hypothesis out there. It has to be the alternative to something. Well, that other hypothesis is known as the null hypothesis, and this is often abbreviated H sub 0. I like to think of the null hypothesis as the skeptic's hypothesis. If the college administrator thinks that hiring more tutors will make the average final exam score go up, the skeptic would come along and say, no, if you hire those tutors, I don't think that the population mean will go up. I think it will stay equal to 75. Okay, so the skeptic doesn't think that the action is going to make any difference. Notice that in the alternative hypothesis, the three options here, less than, greater than, or not equal to, all suggest that the action is causing the population mean to change in some kind of way. Either go up, go down, or not equal to would mean that it just changes one way or the other. The null hypothesis is the one that says the population mean just stays equal to the current value. So that's one of the key differences between the null and the alternative hypotheses. The null hypothesis will always say that the population mean is equal to the current value even after the action is taken, whereas the alternative suggests that the population mean is changing in some kind of way, either going down, going up, or if you're not sure, you might just say not equal to the current value, which means it could change either way. Okay, so we're going to learn how to put these hypotheses to the test. The alternative one is the one that as a researcher we would probably have in mind. If we didn't think our action was going to make a difference, we probably wouldn't bother taking the action in the first place. We would give up and move on. So even though the alternative hypothesis is the one we have in mind, and it's the one that we ultimately want to say something about, it's actually the null hypothesis that we have to put to the test. Okay, mathematically, it's the only one that we can put to the test. You'll see that as we get into some of the examples. So we'll actually put the null hypothesis to the test, and based on what we learn about the null hypothesis, we can then go back and say something about the alternative that we may have had in mind at the very beginning. Okay, there's two different methods that we can use to test hypotheses. One of those methods is known as the traditional method. We're going to learn about the traditional method in this video. There's another method called the p-value method. We'll learn about that one in the next video. The two methods are very similar. There's a lot of overlap, but there is a slight difference between the two. So as we go through these, you'll see the similarities, but you'll also see the difference. Okay, let me just go straight to an example, and I'll kind of show you how you would put a hypothesis to the test using what's known as the traditional method. So it says a researcher invents a new chemical additive that she thinks will make car batteries last longer. Currently, the average life of all car batteries is 36 months. Okay, the first thing that we've got to do is we've got to state our hypotheses. Notice I say hypotheses plural because we're going to state both the alternative and the null hypothesis. So here the researcher thinks that if she puts this new chemical into car batteries, the average car life of batteries will be greater than 36 months, which is the current value. So expressing that mathematically, we might say the population mean, that's Greek letter mu, greater than 36. The skeptic who has the null hypothesis in mind would come along and say, no, I don't think that chemical makes any difference. I think if you put that into car batteries, the average will stay equal to 36. Okay, so again, the null always has equals in it. The alternative never will. The alternative will always have less than, greater than, or not equal to. Okay, so we state the hypotheses. The next thing that we would do is we would have to conduct some kind of experiment or do some kind of research. In a case like this, what you might do is you might just take a sample of cars, let's say 50 cars, give them new car batteries with this chemical additive in it, and tell the people, go out and drive your car around, and when your car battery dies, let me know. So as the people call you back and tell you that their car batteries died, you write down how long it took for that to happen. After you've got all 50 people call you back and tell you how long their car battery lasted, you take those 50 numbers, add them up, divide by 50, you get the sample average. Let's just say, for the sake of this example, it turned out to be 39 months. And while you were waiting and writing down your data as people called you back, you did some research and you found out that the population standard deviation is 8 months. Okay, in this part of the hypothesis testing process, as you do this experiment and research, there's really just 3 key pieces of information that you're ultimately after. Okay, you're going to choose a sample and you're going to get the sample mean. So you need to know the sample mean. And you're also going to need to know your sample size. So in this case, our sample mean was 39, and that came from a sample of 50. And you're also going to want to know the population standard deviation, which is 8 in this case. Now, based on that information, we want to start to think about our hypotheses. Now, you might say, well, 39 is greater than 36, so sure, the chemical seems to work. Well, that might not be true. Maybe it is, but maybe it's not. Okay, we really can't say for sure if it was the chemical that caused the sample average to be greater than 36, or if it was other factors that are going on behind the scenes. Maybe the 50 people that we picked for our sample just take really good care of their cars, park them in the garage. Maybe they don't expose them to extreme weather conditions. Maybe the car batteries lasted longer for those reasons, not because the chemical made any difference. Or maybe it was the chemical that made the difference. Okay, we can't just jump to a quick conclusion here and say 39 is greater than 36, therefore the chemical works. Okay, we've got to dig a little deeper and do some further analysis. Okay, so let's analyze this data a little bit further. So here's one thing that we can say. As long as our sample size has 30 or more in it, then our sample mean is going to have a normal distribution. That's the central limit theorem. So let me draw a bell-shaped curve here representing that normal distribution. Now, remember when we talked about normal distributions, we said that the mean of the distribution will be right in the center of the bell shape. Here's what I'm going to do. I'm going to assume that the null hypothesis is true. Remember, the null hypothesis in this case said that the average is equal to 36. If I assume that's true, then I'm going to put 36 in the center of this distribution. Now, it's actually this assumption about the null hypothesis being true that we're going to put to the test. Okay, and here's how we're going to do that. You know from the central limit theorem that the sample mean should be close to the population mean, at least most of the time. So if we get a sample mean that is close to 36, then we would say, well, that's exactly what we would expect. There doesn't seem to be anything wrong with this assumption that we've made about the null hypothesis being true. But if we get a sample average that is far away from 36, let's say way above 36, then we've got to start to ask ourselves, did this really come from a distribution centered at 36? Let's say you got a sample average that's way out here. There is some area under the curve there, so it could have come from a distribution centered at 36, but it would be a very small chance. If we get a sample average that's way out there, far above 36, maybe it's because when we put the chemical in the batteries, the average actually did go up and is no longer 36, but something greater. So maybe we're getting a sample average way out there because the population average is now way out there. So we've got to kind of make a decision between these two possible scenarios. And here's the way we do that. We put some line here, and we'll say that line is a critical value. If the sample average that we get is beyond that critical value, then we're going to say that's far enough away from 36. We're going to reject the idea that the distribution is centered at 36. In other words, we'll reject the null hypothesis. But if the sample mean that we get is on the left side of that, where it would be close to 36, then we're going to say that's exactly what we would have expected from a distribution centered at 36. Therefore, we will not reject the null hypothesis that says that the mean is equal to 36. So where do we draw that line? That's the question. Well, where we draw the line depends on how much risk we're willing to take in making a mistake if we say reject the null hypothesis. The amount of risk that we're willing to take in rejecting the null hypothesis when we really should not have is known as our level of significance, and it's represented by a Greek letter alpha. In this example, I'm going to choose my alpha value to be 1%. I'm going to take up to a 1% chance that I would reject the null hypothesis by mistake. Now, if you want to take more risk, you can choose 5%. If you want less risk, you can choose a smaller number. Okay, in real life, this level of significance is determined by how much risk you're willing to take. Now in class, we'll just tell you what the value is, but that's what it represents. It's like a risk tolerance factor. So what I do is I will shade 1% of the area in the right tail here. Now I'm shading in the right tail because we have the greater than sign in the alternative hypothesis, which means we're looking for the average to be greater than 36. So that makes this what we call a right-tailed test. Now, that dividing line is going to be the value that separates this 1% from the other 99%. In order for me to find that value, I'm going to have to find the z-score that has a area of 99% to its left in a standard normal distribution. Okay, so if I shaded 1% of the area, that means 99% or 0.9900 in decimal form is that unshaded area to the left. So I'm going to go to my standard normal chart and I'm going to look for 0.9900. Okay, 0.9900 is not in the table. It's in between 9898 and 9901. And it's closer to 9901, so I'm going to use that value, which would be 2.33. So the critical value here is 2.33. So if my sample average has a z-score that is greater than 2.33, then I'm going to say that is far enough away from 36 that I feel comfortable saying that the 36 was a bad assumption and that the distribution is probably centered somewhere above 36. But if the z-score for my sample average is less than 2.33, then I'm going to say, hey, that's close enough to where the 36 is that I don't really see any problem with the assumption that the distribution is still centered at 36. So we're going to convert our sample average into a z-score. You might remember the formula we used to do that. We would take the sample average minus the population mean, which we're assuming to be 36 in this case, and we're dividing that by the standard deviation over the square root of the sample size. Okay, we learned this back in the central limit theorem section, how to convert a sample average into a z-score. Now, if you remember, you might want to break this up into a couple of steps. 39 minus 36 is 3. And then if you did 8 divided by the square root of 50, you would get something like 1.1313. The decimals kind of go on forever. So take the 3 from the numerator, divide by the 1.13137 that goes on. You get 2.65 as that z-score. Well, where is that in terms of our picture? Well, that's on the right side of the critical value in that area that I've shaded. What that means is that this sample average is far enough away from 36 that I feel comfortable saying that was a bad assumption. I don't think the distribution is centered at 36. I think it's probably centered somewhere closer out this way where our sample average ended up. Okay, remember, the sample average should be close to the population average most of the time. So if our sample average is way out there to the right, it's probably because the population average is now way out there to the right. So my conclusion is going to be reject that null hypothesis. Okay, reject the hypothesis that said that the average stayed equal to 36. Therefore, we can say it appears that the chemical does make a difference. Now, I have to say it appears that the chemical makes a difference. I can't say for sure that it does, because remember, there's still a chance, up to a 1% chance, that this sample mean came from a distribution that really is centered at 36. So we have to say something like it appears or the data suggests that the chemical made a difference. Okay, so we would call that a right tail hypothesis test. Here's another example. It says a contractor thinks a new type of insulation will lower heating bills. Right now, without it, the average bill is $178. The contractor installs the new insulation on a sample of 600 homes. Their average bill is $176. Population standard deviation is 13. Is there enough evidence to say that the new insulation works if alpha is equal to 0.05? Okay, so first thing, state the hypotheses. The contractor thinks that the new insulation will lower heating bills from the current value, which is 178. So the alternative hypothesis would be that the average is less than 178. The null hypothesis, which always has the equal sign, would be that the average is equal to 178. Okay, the alternative and the null will always have the same number here because both are based on the current value of the population mean. Okay, let's conduct an experiment and do the research. Okay, so we just read about that. A sample of 60 homes was selected, so that's the sample size. The sample mean, once the new insulation was installed, was 176, and the population standard deviation was 13. Now again, we can't jump to a quick conclusion and say just because 176 is below 178, the new insulation worked. Maybe it did, maybe it didn't. Maybe other factors were the cause for the sample average to go down. Okay, so let's analyze the data. Again, our sample size is big enough that we can say that the sample mean has a normal distribution. Remember, a sample size of 30 or more allows us to say that. I'm going to assume that the null hypothesis is true, so I'm going to assume 178 is in the center of that bell curve. We always assume the null hypothesis is true. Now, this is a left tail test because our alternative hypothesis had the less than sign, so I'm shading in the left tail. I'm looking to see if the average went down. So I shade in the left tail and I label that shaded area as 5% or 0.05 or 0.0500 decimal form. Okay, now once I've got that area shaded, what I'm going to do is I'm going to try to find my critical value. Remember, my critical value will be a z-score that has this much area to its left, in this case 5%. So if we were looking for the z-score that has an area of 0.0500 to its left, we would need to go to the negative side of our chart. Now 0.0500 is not in the chart. It's in between 0.0505 and 0.0495. In fact, it's halfway in between, which hopefully you remember from one of our previous videos that you would average your two z-scores in this case. So those two z-scores are negative 1.64 and negative 1.65. So if I add those two up, divide by 2, I get negative 1.645, which if you wanted to round to negative 1.65, that would be fine. So my shaded area here is to the left of negative 1.645 in a standard normal distribution. Now let me convert the sample average into a z-score. So sample mean is 176 minus population mean, we're assuming is 178. Standard deviation is 13 divided by the square root of the sample size, which is 60. So you can work out the calculation. You should get negative 1.19, which is not in the shaded region. In other words, our sample average is close to the 178 that we assumed was in the center of the distribution. Therefore, we have no reason to believe that the 178 was a bad assumption. So my conclusion here is do not reject the null hypothesis. Okay, if the population mean is 178, you would expect a sample mean close to that, and that's exactly what happened. So there's no reason to believe that the null hypothesis was a bad assumption. So you might say, if you wanted to interpret the conclusion, that it does not appear that the new insulation lowers heating bills. And never soft language, it does not appear. We can't say for sure that it doesn't work, but it doesn't seem to based on the data that we've collected. Okay, so again, that one's called a left tail test because we shaded the left tail. Now let me do one more example here with you. It says a medical journal reports that the average heart rate for all people is 81.0 beats per minute. So BPM is beats per minute. You disagree. You take a sample of 30 people and find their average is 80.0 beats per minute. Population standard deviation is 8 beats per minute. If alpha is equal to 0.05, can you say that the report is wrong? Okay, so we're going to state the hypotheses just like we've always done. Now in this case, it says you disagree. That's kind of a neutral word. It doesn't really suggest that you think that the average is less than 81 or greater than 81. It just says you think it's something different. So this is a case where you use the not equal to sign in your alternative hypothesis. The average not equal to 81. And the null is always going to be equal, so the average equal to 81. Okay, let's conduct the experiment. In this case, we chose 30 people, got that sample's average heart rate, it was 80. And the standard deviation for the population, somehow, some way we found out it was equal to 8. Okay, now for the analysis here, again, we have 30 people in the sample, so the central limit theorem comes into play, and the sample average has a normal distribution. So there's the bell curve. We assume the null hypothesis is true, so we put 81 in the center. Now, in this case, where the alternative hypothesis has the not equal to sign, you're looking to see if the average is less than or greater than 81. Okay, you're kind of looking both ways. So you've got a shade in both tails. Now that alpha value, your level of significance, that represents the total amount of shaded area. So we've split that into two parts. So we're going to take our alpha value, which is 0.05, and divide it by 2, and say that each shaded area has 2.5% of the area under the curve, or 0.0250 in decimal form. So on the left side and the right side, you've got 0.0250 shaded. Now, if you want to get the critical value on the negative side, just go ahead and look up 0.0250 in the standard normal chart and see what the z-score is that has this much area to its left. So we're looking for 0.0250, which is in the chart. Okay, it's one of the few that is. Negative 1.96 would be that z-score. So negative 1.96 is my critical value. Because of the symmetry in the distribution, I could say that the positive one is positive 1.96. Now we convert the sample mean into a z-score. So take the sample average 80 minus what you assume to be the population mean, which is 81, divided by the standard deviation 8 over the square root of 30. That gives you negative 0.68, which again is not in the shaded regions. It's close enough to the center of the distribution, close enough to the 81. So we would say do not reject the null hypothesis here. Okay, now this is known as a two-tailed test because with the not equal to sign, you're looking both below and above 81. You're looking on either side. Now, it turns out with a two-tailed test, you can actually come to the same conclusion by creating a confidence interval. So remember our alpha value, our level of significance was 5%. If we choose a 95% confidence interval, okay, so that level of significance and the confidence level would have to add up to 100% in order for this to work. So we'll need a 95% confidence interval. You might remember that from our last video, where we take the sample average plus or minus the margin of error. And in this case, we know the population standard deviation. So we can use the z-score version of the margin of error formula. For 95% confidence interval, the critical z-score is 1.96. It's not a coincidence that was the critical value in the hypothesis test. So 1.96 times 8 over the square root of 30 gives you 2.9. Take the sample average, 80.0, and do plus or minus with 2.9. When you subtract, you get 77.1. When you add, you get 82.9. Now, 81, which was what the null hypothesis said the population mean is equal to, is inside of that interval. Well, if it's inside the interval, that means you have confidence in that value. If you have confidence in it, you don't want to reject it. So you would reach the same conclusion. Now, if the value from the null hypothesis was outside of the interval, then you would not have confidence in it, and you would reject the null hypothesis in that case. Okay, now this really only works for two-tailed tests. There's ways that you can modify these confidence intervals to make it work for one-tailed tests, but we don't really get into that in this course. It's more complicated than it's worth. Okay, but for a two-tailed test, it works out quite nicely here. That's just another way that you can go about coming to your conclusion. Okay, so this is the traditional method for hypothesis testing. In the next video, we'll learn another method called the p-value method.